Hi guys, so today I will show you uh, how to create structure stiffness. Okay, so let's have this truss. So EI is constant, E is 70 JPa, and area is 1500 mm squared. So here we will create the structure stiffness. Okay, so in creating structure stiffness, we need to identify the the member stiffness in global coordinate system. Okay, which means we will solve it member by member. Okay, so here the question is determine the structure stiffness. Okay, so how to create this structure stiffness. So before you proceed with that, don't forget to identify the or create a free body diagram that will show to you the reaction, the joint loads, and of course the name of the member. So for example here, we can say that this is member 1, member 2, member 3, and of course the reactions. Of course you have here 1, meaning there is displacement along this along x direction. Okay, then you have also 2, and you have also 3, meaning 1 2 3, meaning the number of degree of freedom will be 3, because there will be 3 translation along x at this roller, then x and y at this point. Okay, so we can say here that this is point 1, point 2, point 3, and point 4. Okay, and of course after you are done with putting the translation, you can now proceed with the support reaction. So 1 2 3, then you can go back here, this is number 4, and put this one. Okay, this is slash designate that this is the reaction. Then 5, then you have 6, then you have 7, then you have 8. Okay, and of course you can assign the direction of the member. Let's say this will go like this after putting the load, then this one, this is arrow sound, designate the direction of the member. Okay, so after you are done with this one, you can now create the member stiffness. Okay, so uh, the structure stiffness, so here uh, to generate structure stiffness, okay, which is represented by S, we will determine for each member the global stiffness. Okay, to determine this one, we need to have, we should have the global if stiffness K for each member. Okay, which is represented by K. So, we can now proceed with member 1. For member 1, based on the figure, for member 1, the length is 6. So, you can put here length is equal to 6 meters. Then, based on the figure, what is the value of cosine theta? Cosine theta is 1 and sine theta is 0 because this member goes only along horizontal, right? Or if you are not convinced with this one, you can use the long method. So cosine theta, you should know the coordinates this one. What is the coordinates this one? This is 0 and 8, and this is 6 and 8. So cosine theta is x2 minus x1 over L, which is x2 is this is 0 and 8, this is 6 and 8, yeah. So 6 minus 0 over length, which is 6, is equal to 1. The same is true with sine theta. y2 minus y1 over L, considering this member, y is 8 minus 8 over 6. This is equal to 0. Okay? This is the shortcut one. Now, you can now go to the value of EA over L. Right? So, EA over L. So, what is E? 70 gigapascal. 70 times 1 times 10 to the 6. Then, 0.0015 over 6. This will give you 17,500 kilonewtons per meter. Okay? So, we are not done. Now, we can derive the member stiffness in global coordinate system. Okay? So, we can now proceed. Okay? The member of K1. Remember that we have, what is our formula? We have here cosine squared theta, cosine theta, sine theta. Is it visible? Is it visible? Is still visible? Okay, sorry. What else? Negative cosine squared theta. Then, negative cosine theta, sine theta. Then, of course, the bracket one. Okay, then, cosine theta, sine theta, sine squared theta, negative cosine theta, sine theta, negative sine squared theta, then negative cosine theta, sine theta, negative sine squared theta, cosine squared theta, cosine theta, sine theta. What else? Negative cosine theta, sine theta. Oops, mistake. This is squared. Negative sine squared theta, cosine theta, sine theta, then sine squared theta. Okay, wait. This is negative cosine theta, sine theta, cosine squared. Okay. So, alternate to. Positive, negative, positive, negative, negative, positive, negative, positive. Cosine, sine, sine, negative, negative. So, now we can put, okay, but before that one, since, see since we are considering member 1, what we can put here is we should include the designation of the support reaction and the displacement. Remember that there will be displacement at point 2 because of the load of point 1 at of 2, sorry. Because in the given, I'm sorry, I forgot there is a given here. At point 4, yeah, it's okay. So here, considering member 1, you can put the designation 7, 8, and 1, 2. 7, 8, 7, 8, 2, 3. 7, 8, 2, 3. Okay? And since we want to determine the structural stiffness, we should focus only on member on 2, 3. Okay, remember this 1, 2, 3, this will have loads. This will have loads that will create the movement. There is also load here, this 4, 6, 5, and 7, 8. These are the support reactions. There is no movement because these are the support reaction. It will resist the translation. But here, there is no translation at 1 and there is no translation at 2 and 3. Okay? So, by putting all these values, your K1 will become by the way, there is EA, EA over L here, don't forget. So, 17,500, because this is cosine squared, this is 1. This will become 1. Right? This is 0. This is 1. This is 0. This is 0, 0, 0. All elements that contain sign will become 0. This is 0. This is 1. This is 0. This is 1. This is 0. This is 0. This is 0. This is 0. So meaning, 1 times AA over L, this is 17,500, will give you 17,500, then 0, negative 17,500, then 0, then 0, 0, 0, 0. Then, negative 17,500, 0, 17,500, 0, then 0, 0, 0, 0. Now, don't forget to put the designation 7, 8, 2, 3. So since we are aftering translation at 2 on 3, Sorry, you put also here 7, 8, 2, 3. I forgot. 7, 8, 2, 3. Since our focus will be on the translation of 2, 3, okay, we will have we will cross out 7, 8. So now, the structure stiffness at 1 will become 17,500, 0, 0, 0. And then forget to put 2, 3 and 2, 3. Okay? This is for member 1. Okay? Let's proceed to member 2. So in total, so we can have also or 0, 0, 0, 0, 17,500, 0, 0, 0, 0. 1, 2, 3, 1, 2, 3. Okay? Actually, this is the formal one. But actually, when you combine, you can use also this one. In my previous example, I use only this one. But for formality's sake, I mean not formality, but the proper way to represent is this one. So the structure stiffness, considering member 1, it will be 1, 2, 3 because we focus on the translation on 1, 2, 3. 1, 2, 3. So we can go to member 2. We can here member 2. Member 2. For member 2, here, what is the length? This is 6, this is 8, this is 10 meters. Okay? What is the coordinate? 0, 0. We can do the shortcut and the long cut method. Okay? So for member 2, length, of course, will be 10 meters. Then, cosine theta will be, considering these two, cosine theta is x2 minus x1 over length. So, it will become 8 minus 0 over 10. It will become 0.8. Sin theta will be 6 minus 0 over 10 is equal to 0.6. Okay? And for EA over L, it will change because length is already longer. 70 times 1 times 10 to the 6 times 0.0015 over 10 is equal to 10,500 kilonewtons per meter. So now we can create now the structure stiffness K2. So using the same concept, using the same formula with this one, of course, it will be your responsibility, just put the values, then multiplied by EA over L. Okay? And also, don't forget to write the basis. For example, here in K1, we have here 7812. remember class we are calculating the structure stiffness in able to identify the displacement. Ha? Because having the displacement will give you the enforces. Okay? That is the concept behind. So we are calculating the global stiffness for each, and able to determine the displacement later on. And if we have the displacement, we can use that displacement to determine the displacement for local, for global, for enforces in local and global coordinate system. Okay? So here, it is assumed that there is value of 2, 3 here. Remember, there is the translation of 2, 3, 1, 2, 3 because of the load that we can put here. Okay? For this time, we focus only on the structure stiffness. On my next example, uh, we will now incorporate this structure stiffness to determine the displacement. Okay? So that is the concept behind. Always remember that the number of the translation is actually the number of degrees of freedom. And for each translation, it has equivalent values of forces to be discussed later. So here, for member 2, 1, 4, 2, 3, right? We can put here 1, 4, 2, 3. One, 4, 2, 3. Okay? So now, for K2, it will become 3780, 5040, negative 3740, negative 5040, and so on and so forth. I will just write. So now, what we can learn here is, we focus on 1, 2, 3. We can now cancel out this one. 4. Right? And also 4. Okay? So now, instead of putting back S2 as is it, what we will do now is we will combine the one that we created in member 1 to member 2. So here, at 1, 1, 1, 1, so it's like that. We will add. Okay? So here, note, for S2 is equal to S1 plus K2. This one. This one will be added with this one. Okay? But the same, 1, 2, 3, 1, 2, 3. So, -3780 negative 3780 5040 negative 3780 17,500 plus 3780 5040 negative 5040 5040 and 6720. The same 1 2 3 1 2 3. Take note it's only here that we added y 0 0, everything is 0 except here at how do you call this one, at matrix 2 2, this one only is added here, the rest is the same, so we can now proceed to member 3. For member 3, let's go back here. We are now at this member. So here, cosine is 0 but sine is 1. Going up. So for member 3, L is 8 meters. Cosine theta is 0. Then sine theta is 1. EA over L is equal to 70 times 1 times 10 to the 6 0.0015 over 8 is equal to 13,125 kilonewtons per meter. Okay? So, the same procedure, we can now create another sequence. So here, K3, the same. Member 3 will be 5, 6, 2, 3. Okay? 5, 6, 2, 3. So here, 5, 6, 2, 3. Five, 6, 2, 3. So 5, 6, 2, 3. The same, I'm sorry, but I just made it shortcut, Use this one. Use this one. So, multiplied by EA over L, what will happen is 0, 0, 0, 0. Then 0, 13, 125. 0, negative 13, 125. 0, 0, 0, 0. 0, negative 13, 125. 0, 13, 125. Again, focus on the unknown displacement, which is 1, 2, 3. 1, 2, 3. So, there is no 1, 2, 3 here. We just focus on 2, 3. So, we will cancel out this one. 5, 6. 5, 6. Now, the same. The structure stiffness is now S1 plus S2 plus S3. Okay? So, the values of the structure stiffness will be 1, 2, 3. 1, 2, 3. Huh? You cannot see? Wait. So now, we will add only here 3, 3. Huh? So from this, we will add only 3, 3. 6, 7, 20 plus 13, 1, 2, 5. Okay? So, wait. Sorry, class. So, the structure stiffness for this truss will be 3, 7, 80 minus 3, 7, 80 minus 5,040. You can copy this one eh. Then add only 3, 3. 3, 7, 80 negative 21 to 80 5,040 negative 5,040 5,040. Then 13, 1, 2, 5 plus 6, 7, 20 is 19, 8, 4, 5. So now, what we can see here is this is now the structure stiffness. Okay? So again, to have a recap again, first, make a free body diagram that will represent the joint load, the displacement or the translation, and the reaction. Then after that, you can create the global stiffness for each member. Okay? And always put the designation. Designation. For example here, the unknown displacement will be 1, 2, 3 eh. 1, 2, 3. So, you focus on 1, 2, 3. 1, 2, 3. So, considering member 1, we don't have 1 as part of the matrix, but we have 7, 8, 2, 3, but no problem. 7, 8, 2, 3. But writing the whole structure, will give you this one, 2, 3 for member 1, but you put 1, 2, 3, 1, 2, 3. So, in this structure stiffness at member 1, we have only 17,500 kilonewtons per meter. Okay? Then, for member 2, here, length is 10, cosine, sine, then use the formula. Okay? What formula we should use? Apply this one. This one. Cosine squared, cosine sine, negative cosine sine, and so on and so forth. Okay? So, for member 2, we have here this structure stiffness. Okay? 1, 4, 2, 3, 1, 4, 2, 3. Always go back to your free body diagram. Member 2 is 1, 4, 2, 3. Okay? 1, 4, 2, 3. Then create now the structure stiffness. So, take note, for S2, it will be S1 plus K2. Okay? So, here, for structure stiffness 2, member 2, is the original member stiffness in global plus the one that you have in member 1, this one. So here is 17,500. We add only here 17,500. Okay? For member 3, so I just make it shortcut. 8 cosine 0, sine theta is 1. Then EI is 13,125. Then create now the global stiffness. So again, go back to the free body diagram. Here is 5, 6, 2, 3. 5, 6, 2, 3. Write it. 5, 6, 2, 3. 5, 6, 2, 3. Then remove which is not necessary. Okay? Since our goal is to have structure stiffness that will determine this displacement 1, 2, 3. Focus only on designated 1, 2, 3. Here, there is no 1, so 2, 3, 2, 3, remove 5, 6. So, it's only 13, 1, 2, 5 that will be added here. So, 13, 1, 2, 5 plus 6, 7, 20 will give you 19,845. And this will be now the structure stiffness. So, this value of S will be used to determine the displacement for this 1, 2, 3. Okay? Later on, the next video, I will show to you how to use this structure stiffness to determine the displacement. And later on, this displacement in global coordinate system will be used to determine the displacement in local coordinate system, the forces in local and global coordinate system. Okay? So, thank you for watching. So, wait for another video. Thank you.